Welcome to the Defense and Aerospace Report. I'm Vago Muradian here at the Naval Research Lab in Washington, D.C. in the MeRLIn lab at this great institution that was founded in 1923 to help the Navy develop the best technology in the world for the fleet. This interview should have taken place while we were covering the Navy League's annual Sea Aerospace Conference and Trade Show in Washington, D.C. just a couple of weeks ago, where our coverage was sponsored by Fincantieri, Huntington Ingalls Industries, and Leonardo DRS. And we're here with Dr. Glen Henshaw, who we should have seen while we were at Navy League, and I'm sorry from a schedule standpoint it didn't work. You're the principal investigator for the MeRLIn program, and talk to us a little bit about the program. You guys are it's cat-like. It's really fascinating, as you saw from the footage, about how it moves. Using 3,000 psi hydraulics on something so small. Talk to us about the program and its objectives.
Yep. So the problem we're trying to solve right now is that when the Marine Corps has to enter an enclosed space like a building or a cave, they don't have any good way of figuring out what the interior of that space looks like, who's there, what's there. So they kick the doors down and run in, and sometimes you find enemy combatants, sometimes you find civilians, and sometimes it's a booby trap. So what we're trying to do is build systems that can go into an enclosed space before we have to send in the troops, so that they can understand what's in that space before they run into it.
And what does MeRLIn stand for?
Meso-scale Robotic Locomotion Initiative, which is a very strained acronym, but we really like the MeRLIn name, so we came up with something that fit.
That's very good. No accounting for what can happen when you trap a whole bunch of PhDs in a room. Now, talk to us. The program is about 4 years old. So talk to us about Butch and about Scout and what the next steps of the program are now that you've at least demonstrated that locomotion is not a challenge, although stability still is.
Well, locomotion is a challenge. So both Butch, which is the robot behind me, and Scout, which is the robot we're going to start building this summer, are miniature quadrupeds. And quadruped locomotion is challenging because when you run, you have 2 feet off the ground, or sometimes all 4 feet off the ground, and you have to figure out how to make the robot not fall over when none of the feet are on the ground. So we chose to build a small quadruped because we wanted something that a Marine could fit in their backpack and then throw through a window or throw into a cave or throw out in the jungle if they're in a heavily wooded environment. Building small robots that are highly agile is more challenging than building large robots that are highly agile, because it's easy to get really powerful actuators that are big. It's hard to get really powerful actuators that are small. So Butch is designed specifically to allow us to develop hydraulics where the pistons are the size of a AA battery and the pump is the size of a D-cell battery, so that we can fit a really capable robot in a very small package. Scout, the robot that we're going to be building this summer, is going to be completely self-contained with an onboard pump, and it'll be able to run around the lab, or we have other facilities at NRL that let us test robots in more realistic environments.
And why a quadruped? As we saw in Iraq and Afghanistan, there were you guys actually have a PackBot, one of the iconic ground robots with a lot of mobility over very rough terrain, self-righting features that it had. Some of our allies have shared a ball that you can throw in a room that does have some over rough ground capability. Why go to this sort of why this sort of a challenge, even though it does stretch the bounds of engineering?
So 2 reasons. One is that NRL is a research lab, and we like to stretch the bounds of engineering. That's our charter. But from a practical standpoint, all of the ground robots that we have right now either have tracks or wheels. So PackBot has tracks. We have other robots that are wheeled. A wheeled robot can go over obstacles that are a little bit less than 1/2 the height of the wheel. A tracked robot can go over obstacles that are a little less than 1/2 the length of the track, which means that if you want to go over boulders that are 3 or 4 feet high, you need a track that's 8 feet long. We want robots that can go over any obstacle that a human can go over, but we want it to weigh 5 pounds, and it needs to be small. And the only way that you can get that is either with flying vehicles or with vehicles that have legs. So we chose to go with the leg route. Legged robots can carry a significant amount of payload, and they can stay in place for a long time.
You are a cat owner. Your cat is dramatic abilities to intercept birds in flight. I will let you describe. But you want that tree climbing ability from these systems. Talk to us about how you get to something that, a cat doesn't think twice before it climbs in the tree. It might think a little bit more of the ballistic trajectory required to get a bird. But talk to us a little bit about how you get that, and also you guys are working very hard on claw design, for example, how you do that. Talk to us about the whole package on how you get to where you need to be.
Yeah, so legged robots right now resemble Butch, except they're typically larger. So you have 4 legs, the back is fused so it doesn't articulate, and you typically have ball feet. And those are the robots that we see on YouTube from Boston Dynamics and from others, and that's the design that Butch follows. Eventually, if you want a robot that can really operate in very difficult terrain like a cat, you need to have an articulated spine, so that the hips and the shoulders can rotate with respect to each other, and also the spine flexes, which gives you a much larger range of motion. And you also need feet that can let you climb. So you can think about something like a goat's hoof, which has 2 independent pads, or you can think about something like a dog, which has 5 independent pads, or a cat, which has 5 independent pads plus claws. So someday, we would like to build robots that can do everything a cat can do. Now, there are a lot of challenges with that. We're only solving a few of them right now. We're probably 10, 15 years away from being able to build a cat robot. But you need a spine, you need the right feet, you need the right sensors, and then you need the right control algorithms so that the robot can perform the same motions that a cat or a squirrel does.
One of the, and I didn't mean to minimize, by the way, the challenges associated with locomotion, but you've shown that, whereas stability is a challenge in and of itself. Talk to us about stability, but also shrinking power sources and getting a 3,000 PSI hydraulic system into something that is, maybe 3 inches by 3 inches to get it to fit into this is just monumental. It's one thing to have a hydraulic actuator, whether it's power, 3,000 PSI, whether it's driving an elevator on a ship or any other, rudder machinery or whatever. It's another thing entirely to get it to fit in this. Talk about those dual challenges.
So stability is a challenge. And you can think about this in the way that you walk around. Almost all the time, one of your feet is off the ground. So you're in a controlled fall, essentially. If you didn't put your foot down, you would fall over. Robots have a difficult time stabilizing that way because typically, in order to stabilize a robot, you would want to be able to exert forces anytime you want in any direction you want, and you can't do that with legs. You can only exert forces with the legs that are on the ground. And it took the community a long time to figure out how to solve that problem. We've got a couple of good solutions now that work for sort of horse-like gaits. We don't have any good solutions that really work for cat-like operations, which are a lot more free-form. The cat's, climbing up trees, jumping. We don't know how to solve that problem yet. So we're working on that. But in order to perform those motions, it's not enough to just have the right software. You also have to have actuators that are strong enough and fast enough to let the robot actually perform those actions. Typically, robots use electric motors. Electric motors work really well at a larger size. When you try to get them to a smaller size, they don't have enough power, and the gears turn out to be microscopic, and so they're very fragile. We went with hydraulics because hydraulics are bulletproof. You can get a lot of power out of them, but there are no commercial applications yet for hydraulic systems that are this small. So we had to design and build most of the components ourselves. One of the components that we had to design and build was a hydraulic pump. Typically, if you've seen a hydraulic pump, it might have been on a tractor or a bulldozer and it would weigh 100 pounds. We need one that weighs ounces. So we have one engineer whose one job is to build us a hydraulic pump that's the size of a D-cell battery. It has to operate at very high pressures. 3,000 PSI is typical in the industry, and making something that small, that powerful is a big challenge.
And why 3,000 PSI? Because you talked about, but just as we were getting ready for this, that 1,500 PSI you can do, and that sounds very impressive until you realize it actually falls short for what you need to do. Why do you need that higher pressure?
The more pressure you have, the more power you can get out of the hydraulic pistons. I could get very nerdy and explain why that is. It has to do with the surface area of the piston. Our pistons are very small, the surface area is small, and so the amount of force that the hydraulic fluid is exerting on them has to be high in order to get the instantaneous motions that we want out of the robot. So the more power we have, the more dynamic the robot will be. Sometimes we may actually want to reduce the pressure because it saves energy. We're running off of batteries. But sometimes if you want to jump over a boulder, you really do need that instantaneous power.
In order for the cat to go ballistic.
Yes, exactly. The cat needs to be ballistic.
I just think that is one of the funniest things, lines I believe I've uttered in a long time. A ballistic cat. The Navy is always working on challenging problems. Yeah, in order for any of these two systems to be actually useful, though, you need power management is really the big challenge. And one of the things which I thought was most illuminating is you both use Formula One actuators here, but the problem with the Formula One actuators which solve your problem is they consume vast amounts of power when they're not even doing anything. So talk to us about power management and how much useful dwell or operating time you need to have from this system for it to be operationally useful.
Yeah, so a hydraulic system has three main parts. You have the pump that's providing the power, you have the cylinders that are exerting, that are creating motion, and then you have valves that turn the actuators on and off. Our pump and our cylinders are custom. Our valves are commercially procured. They come from the Formula One car racing industry, and they are small and very, very powerful because the Formula One industry needs small, very powerful valves, but a Formula One car is not power limited because it's got a gasoline engine. So the way that our valves are designed for technical reasons, they draw an enormous amount of power. They're very capable. They can produce very rapid motions, but they draw an enormous amount of power. So in order to get the power usage of our robot, which operates off of batteries and not a car engine, down to the point where it's useful, we need to develop more energy efficient valves. We do have a funded effort to work on that. Starts this fall. So we'll be redesigning valves as well. And at that point, Butch will have a completely custom actuation train.
And how should it have 1 hour of battery life, 2 hours of battery life? How much juice in the tank do you need for this to be operationally useful? Because ultimately, if you're doing this for troops in the field, nobody ever said I want shorter battery, short of life out of anything.
Right. So longer is always going to be better, right? The amount of battery life we get really depends on what we're asking the robot to do. Like the same as a human. You can run a marathon or you can run a 100-yard sprint, but you can't run a marathon at the speed of a 100-yard sprint. So the same thing's going to be true here. There's going to be times when the robot needs to move very fast. There's going to be times when the robot needs to sit still and watch, and the amount of mission life that we're going to get just depends on what the profile is. Right now, with the current valves, 10 to 15 minutes is a really, really good goal. That's a stretch goal for us. I think if we could get operation up to 30 minutes to an hour, there would be some real military utility out of it. Someday, what you'd really like to have is a robot that could go out on patrol with a Marine fire team. And patrols can be 8 hours long, but you're not running for 8 hours. You're often sitting still or moving very, very slowly. So with clever power management, by turning the pump on and off, changing the pressure to be just exactly what we need, and optimizing our gates, I think someday we can get there. We're depending on batteries getting better. They are getting better very quickly, and then we're going to do clever controls engineering to extend the life of the robot.
And it's not just about the robot, right? I mean, that battery pack is also going to have to power sensors, but there's been more progress, hasn't there, in terms of sensors that don't draw a lot of power and have form, fit, and function that you guys can use.
Yeah, there is, and a lot of those actually come from the smartphone industry. So Apple and Samsung, right, have really done us a solid. So 10 years ago, I don't think you could have bought the sensors that we need to put on this robot to make it useful, and now those things are commercially available. The other challenge is getting computers that are small enough but powerful enough so that they can do the number crunching that we need. The human brain is an amazing thing. The cat brain is an amazing thing too. Those are computers that we can't replicate right now. Computers draw a lot more power than the equivalent processing power in a brain does. There are new kinds of computer chips coming out. DARPA sponsored a lot of them. They're called Neuromorphic chips, and they try to mimic what the brain does. They use a lot less power, and we're investigating those here.
You're pioneering a whole bunch of technology that, because the civilian world doesn't have these applications, whether for hydraulic actuators or the pumps or even the cylinders, which you've had to custom manufacture. Society in general has benefited when militaries are solving complex problems like this in ways that we can't even count on a daily basis. As you develop these new actuators, develop these new smaller but very efficient cylinders, stabilization systems, as well as sort of a much smaller hydraulic ecosystem, how does that then translate into the civilian world where, aside from cats that don't have to go to vets because they'll probably still have to go to mechanics somehow then, because I think it would be cool as heck to have one of these as a home security system. But, what are the spillover civilian benefits from some of these technologies?
So robots right now are mostly commercially used in factories, and those are environments that are engineered to be compatible with robots. Legged robots are good for environments that are not designed to be compatible with robots. So environments that you operate in all the time, such as your home, or maybe the most obvious one is if you have a search and rescue or a disaster scenario, you can send robots in to locate survivors, and they have to operate in very challenging environments with lots of rubble and fallen down buildings and so on. Environmental remediation, construction sites, those kinds of environments where you really need legs in order to be able to maneuver. One of the technologies that we're most excited about, though, is just the existence of miniature hydraulics. So right now, almost everybody that's building small mechanisms that need actuators, whether those are robots or anything else, use electric motors. And the reason for that is that electric motors are very conveniently packaged and they're easy to work with. There hasn't been a commercial application for hydraulics. Hydraulics have some advantages over electric motors. They are much more powerful and they're much more robust. They have a longer lifetime as long as you can manage the sealing problems. And we think that there are going to be applications for miniature hydraulics. You can make some of those up. You can imagine that if you wanted aerodynamic surfaces on your car to make it more aerodynamic, you might want to have hydraulic actuators that can change those surfaces. That's actually what Formula One uses them for right now, or for other small high power applications.
And what about the danger associated with 3,000 PSI hydraulics, right? You hear 3,000 PSI, there's always a slight, an X number of hairs always go up on the back of your neck. When you put that much power into such a small package, what's the danger quotient associated with that in the event of a mishap?
Yeah, so it's certainly true. Putting high power hydraulics, if you get a leak, you get 3,000 psi hydraulic fluids leaving that leak for some period of time. But that problem is really true for any technology where you need a lot of power in a small package. And lithium batteries have not the same problem, but they have a problem, which is that they're explosive. And we've had people die from lithium battery explosions. So it's a problem that we have to learn how to engineer safely, but it's not a problem that's unique to this technology.
And one would imagine that because the quantity is smaller, right? I mean, one of the other problems with hydraulics under that pressure is flammability. I guess the solution would be a very small amount of fluid would be required so it would dissipate more quickly, for example, than from a giant accumulator.
Yeah, that's right. So you want to engineer things so that they don't leak, so that they're robust to punctures, but if they do puncture, the amount of hydraulic fluid that we have is quite small, and so I think the threat is quite small.
What is the AI component of this, whether for object recognition, navigation, right? Every challenge, you can make a rover that operates on Mars, it just moves very slowly as opposed to moving quickly and getting itself into trouble. You're looking at something moving quickly over dynamic and difficult terrain. Talk to us about how you do that and how you lick that part of the problem.
Yeah, so there are 3 or 4 areas where you really need good software here. One of them is in the controls, just how do you generate a gate, how do you make the robot not fall over. One of them is understanding what paths the robot can take, so we don't want it to run into a tree, right? So you need good machine vision so that it understands its environment, and that has to happen very, very quickly. It needs to understand where it can place its feet and where it can't. If you're climbing a tree, for instance, where you put your feet is very important. There's been a lot of progress just in the last few years in machine vision in those areas, although most of that progress hasn't been applied to robot motion. So we're trying to take advantage of that and push it where it needs to be pushed. And then above that, you'd really like the Marine who's operating this thing to not have to joystick it. You'd like it to be able to interact with it the same way that it interacts with a military dog, a mom-sniffing dog, for instance, where it takes high-level commands, gestures, understands words, and you can train it to go where you want it to go without needing to keep your head looking at a screen and your hands on a joystick. There are other parts of NRL that work on that research. We're trying to provide them the platforms.
Let me ask a falling resilience question, right? Cats are never daunted by climbing something, and when they fall, they have an extraordinary system of ending up on their feet, but there are also a whole bunch of things that go into that for them to absorb that fall, including padding, bones that are flexible, and here you're dealing with machined or printed metal components that if they do fall, they tend to actually bend or deform, which then interferes with the operation of the system. How are you guys thinking through that part of the problem, short of sort of padding it in case it falls butt first, because I don't know if you're going to have a auto stabilization and righting system that the cat intuitively appears to have. Some excellent research done on that recently to figure out why that happens. How are you guys thinking through that part of the problem?
Yeah, so you're right, cats bounce, right? And there's a couple of reasons for that. One is that muscles are soft, and you're right, aluminum is not. Nobody can build muscles, robotic muscles today. We don't know how to do it. If we did, that would be a huge breakthrough. So what we're doing instead is we have control systems that make the legs compliant. So we're sensing the torque at the joints, and instead of trying to be very rigid, we're trying to make the legs passive to jolts like that. So if it falls, the legs should comply. And that's a technique that's been around for a while. It's been applied sometimes to hydraulics, not a lot, but sometimes, and we have that kind of system here. So if we drop this robot on the floor, it should survive. It will probably be padded at some point when we deploy it, because we would like it to bounce. The real answer to that question is someday we need to get really a lot better at engineering systems that don't rely on rigid components. We need to understand how to do soft engineering.
Now, hydraulic. This has a big, Butch has a big hydraulic reservoir. Scout will have a small hydraulic reservoir. How much fluid do you reasonably need in these lines in order to be able to power that? Because this is overkill, but a small amount that is in, how much fluid do you need? How much fluid are you trying to compress to 3,000 PSI with that D-cell sized pump?
Not very much. So because the pistons are small and the lines are narrow, we don't need that much fluid. I think it's a couple of hundred cc's if I recall correctly. The fluid does need to move very quickly. We have to circulate that fluid quite rapidly, about 1.5 gallons per minute equivalent.
Which is just extraordinary if you think about a small pump and the size of the lines. Now I have to ask you an engineering PhD question. You earned your PhD from the University of Maryland in aerospace engineering. Big Bang Theory fans will tell you that Sheldon Cooper is eternally derisive of everybody who's not a theoretical physicist, but also, why would you have a PhD in engineering? You have a PhD in engineering. Your colleague who's sitting off camera here, without whom this system would not exist, has a PhD in engineering, and both of you seem very well adjusted. He got his from Virginia Tech. There's apparently going to be a cage match later. Sadly, we haven't been invited. So how do you respond to that funny yet idiotic comment always being made by a very popular show that's supposed to be advancing science?
Yeah, so I don't watch Big Bang Theory because it's too painful. My family apparently enjoys it quite a lot, so maybe there's some resemblance there. I don't know. Not to take anything away from theoretical physicists, because those guys are really smart. I really love engineering because it lets us change the world. We can build things that really make a difference in people's lives, and that impact, if you're lucky and you build the right thing and you do it well, can be both dramatic and very, very rapid. So it's sort of an immediate gratification issue.
Yeah, and I'm just going to be honest, I don't really recall any of you eating chili with your hands. So thank you very much for doing this fascinating program. And Glenn, would love to come back and actually see you on the space side of things next time, because you do also the space robotics and which you're doing in partnership with DARPA, and utterly fascinating. Would love to go and actually see the world's largest gravity table that you have just on the other side of that wall.
That'd be great. You're invited.
Thanks very much, Glenn. Really appreciate it.
Thank you.